So in this segment, I want to go into more details concerning some of the examples of easy graphs we already saw. This still relates to section 4.1 of the lecture notes, and in a sense I want to start from scratch just in case some of you have not seen the first video which is on Keats for this. So I'd like to remind you of the graph Cn. That's the n cycle. In fact, I'll do examples in this section only. So let me give you an example of C5. So I want to talk a lot about pentagons in this part. So C5, I can draw it as 5 vertices around a circle, or I can draw it as the graph simply defined by a pentagon. So we take 5 sides, try and draw it as regular as I can, 5-sided pentagon, there we are. We put blobs at the vertices, these are the vertices of our graph, and the sides of the pentagon are the 5 edges of our graph. That is the graph, or it's a representation, I should say, of the graph C5. It doesn't matter whether you prefer a circle, because we're not interested in metric properties, we're just interested in the connectivity between the vertices and the edges. Now I could take the same, well, let me give you another example of a graph which I've mentioned before, and this would be the complete graph on 5 vertices. So this time we add edges so that each of the 5 vertices is connected to every other vertex. Okay, so if we do that, we no longer have C5, but we have the complete graph on 5 vertices called K5. Now what have we done here? We've actually added another pentagon. The inner shape would normally be called a pentagram, but as I want to explain in a moment, as far as the graphs are concerned, it's just another pentagon. So let's just draw the 5 vertices again, if I'm able to, and just draw the pentagon which we see on the inside, the pentagram which we see on the inside. So here's the pentagram, just joining the 5 vertices to each other in a different way. So that's what I added on the inside, but you see, as a graph, it's actually the same graph as the cycle C5, the cycle graph, the 5 cycle. Because let's say if I label the vertices like this around the pentagon, which remember before we added the inside was the cycle C5, I can make those correspond in this picture by, if this is 1 has to connect to 2, so I have to put the 2 there, and then 2, or I could have put it there, it doesn't matter. And then the 2 connects to, say, the 3, so we put the 3 there, and the 4 there, and the 5 there. I just need to make sure, if I want to compare the outer cycle here with the inner pentagram here, I just make sure that we have the same connectivity. So what I'm really trying to tell you is that the pentagon, as I draw it as a pentagon, as a graph is isomorphic to this configuration here. Okay, so maybe I'll define formally isomorphism of graphs later, but the idea is that I can map the vertices of the outside pentagon to the vertices of the pentagram, so that any 2 vertices, if they were connected by an edge before, they're still connected by an edge. They're connected by an edge before, if and only if they're connected by an edge afterwards. So you see 1 and 2 are connected by an edge, and they're connected by an edge. 1 and 3 are not connected, were not connected by an edge on the outside, and they're not here. So this is really just another version of C5. But what I did is I've sort of taken that and added it to the original C5, and I get another graph which is K5. I could actually add it in a more complicated way by sort of thinking of the thing as in 3 dimensions and putting the pentagram on top somehow. So what I really mean by that is that I'm going to draw the original pentagon again, yet again, here. But this time I'm going to make the pentagram smaller, and I'm going to add these spokes here so that I'm able to get 5 vertices closer together, which will be the vertices of my pentagram. on the left. Okay, I'm still going to have these 5 vertices around the outside. And now I'm just going to put in my pentagram on the inside. And that's another graph. It's completely different. Let's call this graph P. It's actually called the Pettison graph. Pettison graph. And you say it's formed by just adding, if you like, 2 pentagon graphs together and adding these 5 spokes. Okay, so let's just remind us, let's just count the number of vertices. It has 10 vertices because we've taken 5 plus 5. How many edges does it have? Well, it has, we had the original, we have the 5 on the outside, the 5 of the pentagram, but we've added 5 spokes. So it actually has 15 edges. Okay, 15 edges. It's an example of a regular graph, as of course the other 2 were, because all the vertices have the same degree. They're all going to have degree 3. Let me write, I'm going to change pens now. So this is an example of a regular graph. It's regular. Because regular means that all the vertices have the same degree. All vertices have the same degree, which here is 3. In the 2 graphs on the left, it's 2, of course. But in the Pedestrian graph, they all have degree 3. And of course, that gives you another way of counting the edges, because if you have 10 vertices, they all have degree 3. That would ostensibly give you 30 edges, but you have to divide by 2, so you get the 15 edges. That's the Pedestrian graph. Let me emphasize that in this particular talk, I want to restrict myself to simple graphs. So in this section, all graphs in this talk will be simple. So for the moment, let's say all graphs will be simple. Let's say in this section 411. Simple means that, remember I defined this in the first lecture, simple means that there are no loops and no multiple edges. And that makes things easier. That's what simple means. Okay, now let me describe this Pettison graph in a different way that corresponds more closely to the way I defined it in the lecture notes. It's defined actually in section 4.1 of the lecture notes in terms of subsets of a set with 5, in terms of subsets consisting of 2 elements in a set of 5 elements, and that's all related to the graph K5, because here we have 5, we have a set of 5 numbers, and any edge in K5 connects 2 of those numbers, and therefore corresponds to a subset of the set 1 to 5. For example, this edge here that joins 1 and 2, I can think of that as representing a subset, curly brackets 1, 2, which is a subset inside the set of 5 elements, which are the 5 vertices. And the point is I have all possible subsets because I have all possible 10 edges. So let me use that idea and sort of give you a different way of thinking about the Pettison graph, if I can. It's a bit mucky. Okay, so let me try and say it like this. Let me draw again K5. Okay, so K5 is the complete graph on 5 vertices. So here's a picture of K5, a dirty great big pentagon. So let's see what I can do. K5. So here we have the 5 vertices around the pentagon. Let me label the vertices again. 1, 2, 3, 4, 5. That would be C5, but then I have the extra edges I put in, corresponding with pentagram. So now I have K5. This is the graph K5 in which any 2 vertices from 5 joined by an edge. Now, as I just said before, but let me write it down. Any edge of K5, any edge of K5 defines what I'm going to call a 2 subset. That's just a neat way of saying a subset with 2 elements of the set 1, 2, 3, 4, 5. Because, I mean, that's how we think of the edge of a simple graph. We just have to choose 2 vertices to define the edge. The point is, for K5, we can take any subset because we include all possible edges joining any 2 vertices. Okay. Now, what I'm going to do here is I'm going to try and define the Pettison graph in a slightly different way, a more sort of combinatorial way. And a vertex of the Pettison graph will correspond to one of these subsets. So I won't call it the Pettison graph, but that's what it will be. So we shall define a graph, which will be the Pettison graph, with a red vertex, if I can find a red pen, with a red vertex, or maybe a green, I think I've got more green in my repertoire, with a green vertex for each such subset. Or equivalently for each edge of K5. So in other words, I'm going to assign to each edge of K5 a green vertex. So I'm going to put that vertex in the middle of the edge. So you see the edges around the outside, each of those corresponds to a green vertex, which are plonked down in the middle. And then I've also got 5 edges from the pentagram, and these will also correspond to 5 vertices. And these are going to be the vertices of my Pedestrian graph. It's going to look rather different to begin with from the picture I had on the first sheet. So those are the 10 vertices that correspond to the 10 subsets with 2 elements, or the 10 edges of K5. But now here's the key point. I don't have a graph yet, I just have 10 vertices. To define a graph, we need the vertex set, and we need to know the rule for the edges. It doesn't matter how the graph looks like in the plane or in 3-dimensional space or whatever, that's irrelevant. We just need to know the connectivity. We need to know when 2 vertices are joined. That's what defines the essence of a graph. Okay, so we're going to say here that two green vertices, 2 of these new vertices, will be joined, or about to be joined, if and only if the corresponding subsets do not intersect. Now, you see, what does that mean? I mean, what are these subsets? Well, as I explained before, I mean, this green vertex here, that corresponds to the edge 1, 2. So that really corresponds to the subset 1, 2. Whereas this edge here, this corresponds to the subset 3, 4. So in particular, this does not intersect 1, 2. So in the new scheme of things, this vertex will be joined to this vertex. Okay, I probably should have started on the inside first. So this green vertex here corresponds to the subset 3, 5, or the edge 3, 5, K5. And this does not, it does intersect this edge here. No, it doesn't. It doesn't intersect this edge here. This vertex here corresponds to 2, 4. And these two subsets do not intersect. Another way of saying that is that the two edges do not have a vertex in common in K5. So the idea is that in this new graph, which is going to be green, these two vertices are joined together. Similarly, you'll see that these two are joined together, these two are joined together, these two are joined together, and those two are joined together. Okay? But I haven't finished yet, because I've also got the example I did before. This vertex 1, 2 has to be joined to this vertex 3, 4. Again, I don't want to mess things up by going through the middle, so let me just curve as if I'm curving a ball in playing snooker and billiards. I'm going to curve that around the outside, and you can see similarly that these two vertices will be joined together because the corresponding edges in K5, that means this edge here, this edge here, and this edge here, they do not intersect. So that allows me to join this green vertex here to this one here. Similarly, it's going to be obviously very symmetric. So similarly, these two are joined. You begin to see, I think, what's going to happen. These two are joined. And finally, these two are joined. Okay. Now, I still haven't quite finished. Because you see what I've got now. I've got the pentagon, I've got a pentagon, and I've got a pentagram, albeit a curved pentagram. Okay, so I'm almost there. I'm almost at the Pettison graph, but the Pettison graph will join the pentagram, join these 5 vertices on the inside to the 5 on the outside. And that's going to happen now because we also notice, if we go back to this vertex corresponding to 1, 2, of course, 1, 2, there are 3 subsets that doesn't intersect. There's the subset 3, 4, there's the subset 4, 5, and there's the subset 3, let's do that again. There's the subset 3, 4, 4, 5, and 3, 5, but I haven't yet joined 1, 2 to 3, 5. Okay, and maybe I should use different colours so as not to confuse things. So I need to join 1, 2 to 3, 5, and I need to join these two. You see, obviously it's going to be working out. I need to join these two, and I'm going to join 1, 2, 3. I'm going to join these two, and I'm going to join finally these two. Okay, so each vertex of the pentagram has been joined to each vertex of the pentagon, and in terms, I mean, it looks very different. So in other words, we've now got 15 edges. Okay, so I've got a total of 15 edges. We've got some that are pink and some that are green. Okay, but the actual configuration is the same as that of the Pettison graph because I've taken a pentagon, albeit now that's on the inside. I've taken a pentagram and I've stuck them together with 5 pink spokes. So, the 15 edges includes, let's say, 5 the spokes, which I had in the previous diagram, but these are now drawn in a different position, and they've been drawn pink. And that is the Pedestrian. Okay, but the point is I've shown it to you, in a sense, it's been constructed from K5 using a fairly systematic algebraic operation. In fact, we sort of converted each edge of K5 into a vertex, and then we could have just joined those vertices if the edges intersected, but we took the opposite rule, what's called the complement rule, we joined those two vertices if the two edges of K5 did not intersect. So we've been using these rules, and using that we've constructed really from K5, which is a very basic example in graph theory, we've come up quite naturally with this other example of a more complicated graph called the Pettison graph, which has 10 vertices and 15 edges. So that example, if you found that a bit complicated, that example is mentioned in terms of the subsets of 5 elements. It's mentioned in the example in section 1.4 of the notes. Now, there's one other thing I want to do with this example, and this is related to the concept of isomorphism, which I mentioned. Namely, I want to give you another representation. You've already seen about 3 representations of the Pedestrian graph, or 3, at least 2 different representations. The nicest one, of course, being the classic representation being this one here, of the pentagram inside the pentagon. That's the easiest way to remember it, and probably the easiest way to draw it. Don't forget that when we're doing graphs, these graphs can never be drawn in the plane without some crossings, without edge crossings which are not vertices. So the vertices are indicated by the big blobs. If 2 edges cross, and here there are 5 crosses on the inside, there's a little sort of mini pentagon on the inside, but these crossings are not vertices, obviously. It's just that I can't draw it in the plane without such crossings. If I visualize this in 3 dimensions, I can manage it. Similarly, obviously, in this rather more complicated looking diagram, there are lots of crossings, these pink, the green crossings here and the pink over the green, but these are not vertices. The only vertices are the 10 green blobs. So I want to give you another representation. I'll just start afresh. So let me just give you another picture of the Pettison graph, another representation, and I want to finish with I want to define what we mean by an isomorphism of graphs. There's a delay on the camera, which makes it hard to straighten things. So here is the let's see, I'll start with a lighter pen. So here is the representation I want to talk about, and rather than drawing a pentagon, which is a bit tricky to get the angles right, I'm going to start with a hexagon. So here's a regular, not quite regular, here's an attempt to draw a regular hexagon, which is a bit easier, I think, to do it. Here's a hexagon, and let's emphasize the vertices of the hexagon, which will be some of the vertices of my graph. So I want to define what looks initially to be a rather different graph that starts with a hexagon. And then I'm going to draw in the 3 diagonals of the hexagon. I'm going to make them curved. 3 diagonals. I'm going to construct, if I drew them straight, they just intersect in the middle. I want to leave a sort of triangle in the middle. Now, these intersections will not be vertices. These 3 intersections, these are not vertices. But sequentially, I want to construct the Pettison graph, so I need 4 more vertices. And these 4 more vertices will be 1 here, 1 here, 1 here, and then I fit a Y, if you like, into the middle. And this middle point is a vertex. So now I do have 10 vertices. This will be actually the Pettison graph, but I've got to explain to you why this is isomorphic to the Pettison graph. And I'll define isomorphism at the end, but I want to sort of define it by the example. So my claim here is that how many edges are there, first of all? Let's say, well, this is a regular graph. It's a regular graph again, with degree, all the degrees are equal to 3. All the vertex degrees are equal to 3, all degrees 3. That means that it has 30 edges. Sorry, not 30 edges, 15 edges. 30 divided by 2. Okay, so it has the correct number of vertices and the correct number, and count them up if you don't believe me, and the correct number of edges. That's the Pettison graph, but there's one wouldn't think, I think, initially that this is effectively the same graph. It certainly doesn't look like the same graph. But what I'm claiming is that if I label the vertices, and I can actually relate the vertices of the Pettison graph with these 10 vertices, so that two vertices in the previous picture are joined if and only if they're joined in this picture. That's the concept of isomorphism. And one way of doing that would be to label the vertices of this graph. I make a start by subsets of 1, 2, 3, 4. Okay, so if I label, let me use abbreviated notate. Well, down the bottom, I don't know what vertex. I think this vertex is going to correspond to the vertex. I'm not sure. Let me label this vertex 1, 2, which really means the subset 1, 2. Remember, the Pettison graph is labelled with 2 subsets of 5 elements. And the idea is I want to label adjacent vertices, 2 vertices are called adjacent if they're joined by an edge, by subsets which don't intersect 1, 2. So that means I can have to choose them from 3, 4, 5. So I could label this 3, 4, this could be 3, 5, and this would be 4, 5. And then you see I can keep going. I need to look at 3, 4. That leaves me 1, 2, and 5. So this could be 1, 5 here, and this could be 2, 5. I'm still sticking to the rule that adjacent vertices correspond to subsets. Remember, these 2 numbers really represent a subset with no 2 elements in common. Okay. The point is I can do the whole picture that way. I may as well finish it. I've got so far already. So 1, 5, 3, 4. I've got 3, 4, 2. So I could put 2, 3 here and 2, 4 here. Now I can't put 2, 4 here because I've got a 4, 5. So that was a mistake. So I better put 2, 3 here and 2, 4 here. Hopefully that works. Right, yes, it works. 2, 4 doesn't intersect this. 2, 4 doesn't intersect that. 2, 3 doesn't intersect that. So far, so good, I think. Now let's look at the 2, 3. It should also be automatic now. 2, 3, we've got 1, 4, 1, 5. We're missing 1, 4 here. And I think have I labelled all of them? I've now got my 10 subsets. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've missed the one in the middle. But hopefully that will be automatic. What am I missing? I'm missing a 1 and a 3. Okay, so what I've done here is I've labelled the 10 vertices consistent with the rule that defines the Pettison graph. Namely, each vertex of the Pettison graph corresponds to a subset of 2 elements. And the rule is that 2 edges are joined, so 2 vertices are joined by an edge if and only if the subsets do not intersect. And if you check, you'll find that no 2 adjacent subsets, if you like, no 2 adjacent subsets have a number in common. I've done it correctly. Okay, so that proves that this is isomorphic. This configuration is isomorphic to the Pettison graph. To say isomorphic to Pettison. Really is Pettison. Let me define the notion of, I'm going to give you another proof that they're equivalent or isomorphic graphs, but let me define the notion of isomorphism. And this will be for simple graphs. The definition is a tiny bit more complicated if the graph is not simple, but you can read that in the notes. So definition, 2 graphs. Now what is a graph? A graph, called one of them G1, consists of a vertex set and an edge set. These are simple graphs, so I can just talk about the edge set, with a rule that tells you when 2 vertices are joined by an edge. I mean, the edge set is a subset of the 2 subsets of V. And the second graph with a vertex set V2 and an edge set V2. So 2 graphs are said to be isomorphic. Isomorphic. If there exists a bijection of their bijective correspondence between their vertex sets. So there exists a bijective mapping F from V1 to V2. So we can map all the vertices of the first graph, each vertex of the first graph to the vertex of the second graph, with the property that connectivity is preserved. So such that UV is an edge in the first graph, so UV is in E1, that means the subset consisting of U and V, the unordered subset consisting of UV is in E1, if and only if their images form an edge. That means F of U, F of V is an edge in the second graph. That's the notion of isomorphism. And essentially that's what I've shown here. Because the rule whether or not two vertices form an edge was given, a bit confusing here because there are also subsets used in a different sense, but two vertices form an edge, that was a rule that corresponded to the intersection when I'd labelled the vertices by these subsets, corresponding to the intersection of those subsets. So we've actually proved that this graph is isomorphic to the Pettison graph. Okay, well, I'm going to give you a sort of more hands-on, if I can manage it, more convincing perhaps proof that this is the same as the Pettison graph. Remember, the Pettison graph is normally thought of as this this thing here, the pentagram inside the pentagon with the 5 spokes. Why are these two graphs isomorphic? Well, what I've got to do, you see, is I've got to try and convert the a hexagon around the outside into a pentagon. You know, in the standard representation of the Pettison, I have a pentagon around the outside, not a hexagon. And the way I'm going to do that is I'm going to take this edge here, this curved edge, this curved diagonal here, I'm going to bring it outside down the bottom into this blue edge. Okay, so what I've effectively done is I've replaced these two vertices now go on the inside, and I've replaced two vertices by one. So if I leave these edges where they are, make them blue, I've now got a pentagon. Okay, so these are going to stay on the outside, they're going to stay blue. What I've done is this has now been eliminated. I've got to do something on the inside, I haven't come to that yet. I've eliminated that, replaced it by the blue thing. What I'm going to do here is let's call these vertices here, well, I just forget the names here, the subset names. Let me call this sort of A, B, O, because it's in the middle, C. Well, C has already gone down here, so C has been replaced by that blue vertex there. I'm going to pull this Y downwards so that the O goes outside here. So I'm going to pull this down and put the O there. So I'll make this now blue. The blue are going to be the final positions. This stays, that's an O. And I'm going to push the A up here, make it blue. So A is going to go up here, and B is going to go there. So it's still, A is still going to be on this edge, but it's been shoved up there, and B is going to be shoved up there. And then my Y, this is the O, there's the A and the B. I've switched it over, so the Y is going to become, just look at the blue, is, that's going to be, the Y is sort of like that. Should have drawn it more straight as a Y. Okay, but I've got the same configuration here. And you see what I've got here is I've got my pentagon around the outside, and I've eliminated all this stuff, all this Y on the inside, and I've got 1, or inside the pentagon, I've got my 5 vertices, which will be the 5 vertices of the pentagram. So you see, they're all related to the spokes. Let me draw the spokes in pink, which is what I used before. So there's one spoke, here's another spoke. So it's going to join the pentagon to the pentagram. There are my 5 spokes. And these edges I'm leaving as they were, so they're going to remain as edges, but they're now in blue. And if you look at what, it looks a bit of a mess, but if you look at what I've got on the inside here, it is actually a pentagram. Let's just draw that separately. And I think I'll just draw it in separately on the right, and you'll see that we really do have the Pettison graph. So we've certainly got the pentagon around the outside, and on the inside we have this, I'm just going to draw, we've got O, put it here, we've got O there, and we have these two things going up there to B and A, and then we have these, push it up a little bit, these other 2 vertices here, and we have that joined to that, that joined to that, and that joined to that. Okay, and that is a pentagram. That's what we have on the inside. So we do have the Pettison graph. I've converted this hexagonal form with the funny triangle and the Y in the middle to the Pettison graph, in which we have the bit of imagination is needed here, but we've got pentagon around the outside, and we've got pentagram on the inside, and these are joined together with the pink spokes. Okay, so that's the Pettison graph is a very useful example because it's less simple than the other graphs we've seen so far. And what I really, the usefulness of this example is to illustrate the notion of isomorphism. You can have graphs that look very different. I mean, this hexagonal configuration really looked very different from the classical Pettison drawing, but they represent the same graph, essentially the same graph. The representation in the plane looks very different. They both have crossings which aren't really vertices, but the graphs are really the same mathematical object. Okay, in the next segment I want to talk about paths in graphs, connecting different ways of travelling from one vertex to another.